Now that we have seen what policy is and in general, a stochastic version of this policy, it's worthwhile now starting to discuss a very important kind of definition, which is actually called value functions. No matter what, algorithms will actually involve value functions, will try to estimate value functions for either states or states and actions in order for them to be able to move into a better objective. And that objective is a policy, a better policy than one they were before. So as we will see, these algorithms are going to be iterative, recursive in nature, and therefore we need to have these functions to define these functions, because these are what they will try to sort of base their decisions to go into a better policy. So we will start with a so-called state value function. And we will symbolize it, this value function, with a small letter v, subscript pi, and with an argument of s. So s is evidently any state that we have in the system, and pi is the policy that we will follow being in this kind of state, s, and v is the name of the value function. All right, so we will now write the definition. The definition is that the v pi of s is an expectation, another expectation, over policies pi of the return g at time instant t, given that we are at this moment in S. So it is effectively the average of all returns that we can get by being in that kind of state. So as the name implies, state value is a function that gives us the value of being in state S. Okay, so we can actually write this expectation as the expectation. We can replace the gt with what we have seen earlier as a summation from k is equal to 0 to infinity gamma k r t plus 1 plus k, given st is equal to s. And we can actually write this as the expectation over policy pi of rt plus 1 plus gamma rt plus 2 plus gamma squared rt plus 3 plus and so on, given st is equal to s. And we can actually write this as the expectation over pi of rt plus 1 plus gamma rt plus 2 plus gamma rt plus 3 plus and so on, given st is equal to s. And actually what we can see here, we can actually see this is effectively the return gt plus 1. And actually we can show, although this derivation of this will not be shown, we can show nevertheless that the Vp of s is the expectation over pi of the instantaneous reward rt plus 1 plus Vp of s prime. And this Vp of s prime came from writing this return at t and connected it to the return that we will be getting at the next time, in the next, if you like, state, given st is equal to s. And this is a very, very important equation that was derived from Bellman. And it's actually, because its expectation is Bellman, is called Bellman expectation equation. a Bellman expectation equation. All right, and effectively what it does allow us to do is allow us to compute the state value function from state value functions of next states and so on. So it actually defines, if you like, some way of calculation by looking at this equation in a tree form. It's actually easier to see. So if we are in, let's say, in state S, we will be denoting as actions nodes with solid color, black in this case. So these are all the possible actions, and each action will lead us to a number of possible future states. Let me call these future states in general S prime. And this is effectively the, over here we have taking, let's say, an action in general A. The policy is the one that mapped the state to a number of actions. Potentially the policy is stochastic. So we effectively ended up taking an action, and that action, the environment is stochastic, and that stochasticity of the environment leads us to not just one, but more than one out of not just the intended, but we could end up like in the grid world in any other cell given the transition model of the MDP problem we are dealing with. So this is actually called, it's actually a very useful representation of the calculation of what this equation kind of represents. And this is actually called backup diagrams. For the state value function VP. And it's called actually backup diagram because it allows us to calculate from the state value function of subsequent states the value function of the current state. So we'll use this kind of equation over here to do that and see, if you like, a numerical example now on how this calculation is actually happening. Before going into a specific example, I think it's worthwhile kind of clarifying something that, in passing, as we sort of discussed the state value function, we have mentioned like this expectation over policy pi. And, there's a kind of some form of confusion that may arise from the fact that earlier we have talked about stochastic and deterministic policies. So I want to clarify this point before going into this kind of numerical example. So we may actually have the term, to clarify first the term stochastic policy. In the case specifically in this kind of a grid world problem we have here, we may have this kind of policy that we called pi of A given S. And this policy could be 0.25, 0.25, and so on, like 1/4, in other words. An equiprobable selection of actions for up, down, left, and right, for example. Okay, so this effectively, for any state, I'm able to select from any of the 4 possible actions. And this is what actually we called a stochastic policy, and as earlier, and as compared to a deterministic, which in this case action, which in this case there's going to be only one action that can be taken for a specific state. All right, so that's basically the starting kind of point of this kind of discussion. So when we take the expectation of a policy pi, I think it's worthwhile clarifying that we definitely do not mean an expectation over pi, but we mean an expectation that pi is a dependency, almost conditioned on. So we should actually see the pi after the given symbol over here. Let's try to make it a bit sort of a bit more explicit. So by writing that stochastic policy, and I think it's best not to use stochastic so much to attach it to policy, but to attach it to the MDP, does not make the MDP stochastic. So a stochastic policy, like for example, every time that we have, let's say with 1/4 probability, we sample an action out of this kind of a uniform probability, in this case, distribution. Let's say we sample the action up, let's say, and we are in state S11. We may actually have a deterministic MDP problem, which means that an up action in state 1 S11 will actually deterministically take us to state S12. Okay, so in this example, I think it's sufficient to support that kind of argument, that a stochastic policy does not make the MDP stochastic. The MDP is stochastic. That's why we call stochastic MDPs. Is made stochastic by the transition model. And in that grid world problem that we have, the transition model was this. So whatever action we select, we will go to the desired action with probability 0.8, and on other actions, left and right, on the other states with probability 0.1. So it is really the unreliability of the transition of the action that is actually make that MDP problem stochastic. Okay, so when we take this expectation, I think it's in other textbooks you will see this expectation, something which I like a bit better than the Sutton's notation that I have adopted over here, is over S prime. So it's expectation over S prime that is sampled out of the probability distribution of S prime comma R given S comma A. And this is effectively can also be written as an expectation over S prime with a probability of S prime comma R given S comma pi of A given S. So this is this is where you see the dependency on this kind of policy pi. But as we discussed, even if this policy is stochastic, if this probability distribution is not, in other words, in other words, what I mean is that let's make it a bit more specific. If the transition model, the transition model of S prime comma R given S comma A is 1 for the specific action, we have taken, the MDP is deterministic. And if it is less than 1, then the MDP is stochastic, which means that this S prime here, we have multiplicity of S primes that we may end up on as compared to deterministic, which is we have the specific S prime always following the S using one of the actions that we have selected, even if this action is taking out itself out of is sampled itself out of a probability distribution.